Omega Hebron logic, or OHL, is function-free Hebron logic. Like FHL, there are no function constants. But unlike FHL, we can have infinitely many object constants. And recall that a logic is compact if and only if every unsatisfiable set of sentences has a finite unsatisfiable subset. Unlike propositional logic in FHL, OHL is not compact. There's an infinite set of sentences that is unsatisfiable, yet every finite subset is satisfiable. Suppose that the signature for a language contains the object constants 1, 2, 3, and so forth, and the unary relation constant p. We take the sentences p of 1, p of 2, p of 3, p of 4, p of 5, and so forth. And then we add the single sentence, there exists an x, not p of x. So that's clearly unsatisfiable. Our ground atoms say that p is true of everything, but our existentially quantified sentence says there's something for which p is not true. However, if we were to remove any single one of these sentences, the set as a whole would be satisfiable, and therefore every finite subset is satisfiable. Okay, although it's not compact, OHL is well behaved in one important way. In particular, the question of unsatisfiability for finite sets of sentences is semi-decidable. That is, there's a procedure that takes a finite set of sentences in OHL as argument and is guaranteed to halt in a finite amount of time with a positive answer if the set is unsatisfiable. The procedure may halt with a negative answer. However, this is not guaranteed. If the input set is satisfiable, the procedure might possibly run forever. Okay, the first step of the procedure is to convert our sentences, let's call them delta, to pre-next form using the technique we just talked about in the section on finite Hebron logic. We then ground the result, and finally we examine finite subsets of the grounding for unsatisfiability. Unfortunately, the grounding technique for FHL does not quite work for OHL, since we can have infinitely many object constants in OHL. In dealing with an existentially quantified sentence, we would have to generate an infinitely large disjunction, and the sentences of infinite size are not permitted in our language. Fortunately, there's an alternative form of grounding called omega grounding, which serves our purpose without this defect. It's a little more complicated, however. Okay, so here's the omega grounding. Once we have a set delta of sentences in prenext form, we compute the omega grounding as follows. We start with our set delta, an empty set lambda, and an empty set gamma. And we repeatedly apply the following transformations to the sentences in delta one at a time, processing sentences in the order in which they were added to delta. Our first rule here deals with ground sentences. If a sentence phi in delta is ground, we would simply remove it from delta and add it to gamma, same as with FHL. If our sentence is universally quantified, we remove it from delta, add it to lambda, and also add all instances of the target for each constant that appears in any of our data sets so far. And if our sentence is existentially quantified, we remove it from delta and add an instance of the target for some brand new unused constant. There's always got to be an unused constant. At each point in time, we've only finitely many sentences, while the language has infinitely many constants. So we just take any one of the ones that has not yet been used. We also add to delta instances of the targets of all universally quantified sentences in lambda using this new constant. Here it's called tau. If delta ever becomes empty, the process terminates. In any case, the omega grounding of the initial delta is the union of all the gamma sub I sets. Okay, let's look at an example with a set of sentences shown here. We have one ground sentence, one universally quantified sentence, and one existentially quantified sentence. All are in prenext form. Computation goes as follows. First sentence is ground, so we remove it from our input set and add it to gamma. Second sentence is universally quantified, so we add it to lambda, and we replace it on delta with a copy with the single object constant we have, namely 1, substituted for the universally quantified variable. Next, we focus on the existential sentence. We drop the sentence from delta and add an instance in its place. Here we have replaced the existential variable with the previously unused constant 2. We also use 2 in another instantiation of the quantified sentence in lambda. Okay, at this point, everything in delta is ground, so we just move all the sentences down to gamma. At this point, since we have run out of sentences in delta, the procedure's finished, and gamma 6 here is the omega grounding for the initial set of sentences. Okay, note that when there's an existentially quantified sentence nested within a universally quantified sentence, the result of this procedure can be infinite in size. Okay, let's look at this example. Set of sentences here is shown here is of this sort. Okay, the procedure goes as follows. For a sentence is ground, so we remove it from delta and add it to gamma. The next sentence is universally quantified, so we add it to lambda and replace it in delta with a copy for each constant mentioned in our sentences. In this case, there's just the one constant, namely 1. Next, we ground the existential sentence using a new constant, in this case 2, and add that result to delta. We also add a corresponding instance of the universally quantified sentence in lambda. Our ground sentence is then moved to gamma. Again, we ground our existential sentence, in this case using the constant 3. And again, we instantiate the universally quantified sentence in lambda. As before, we move the ground sentence to gamma. The construction in this case goes on repeatedly. The union of this infinite set of gamma sub I sets is the omega grounding for delta. Although the set in principle is finite, we don't actually need to compute the entire grounding, just subsets of increasing size. Okay, so now note that the omega grounding for a finite set of OHL sentences is all ground. We know that if the set of a ground sentence is unsatisfiable, then there must be a finite subset that's unsatisfiable. Hence, to determine unsatisfiability, we can just check finite subsets of our omega grounding as it is being generated. If the set is unsatisfiable, we will eventually encounter an unsatisfiable set in this process. Otherwise, it might run forever. In any case, it demonstrates the semi-decidability of OHL.